Welcome back, network explorers and data scientists. Today, we're stepping beyond the boundaries of traditional data structures to dive into one of the most exciting frontiers in artificial intelligence, graph neural networks, or GNNs. If you work with social networks, recommendation systems, molecular structures, or any kind of connected data, GNNs are about to become your new best friend. In this video, we'll connect the dots and show you how AI can truly understand relationships and connections, not just isolated data points. Let's get started and see why GNNs are revolutionizing the way we interpret complex, interconnected information. Most AI models you've heard of are designed for grid-like data, such as images, or for sequences, like text. But the world isn't always so neatly organized. Much of our data is fundamentally relational. Think of social networks, molecules, transportation systems, and knowledge graphs. Graph neural networks are specifically designed to work with this kind of interconnected data. Imagine an AI that doesn't just see individual data points, but truly understands how they're connected and how information flows between them. That's the power of GNNs, and it opens up a whole new world of possibilities. Let's start with the basics. In graph theory, a graph is made up of nodes, also called vertices, which represent entities like users, atoms, or cities. The edges are the relationships between these entities, such as friendships, chemical bonds, or roads. Each node and edge can also have features, which are pieces of information attached to them. You see graphs every day: social networks, recommendation systems, molecules in chemistry, transportation routes, and knowledge graphs. The challenge? Traditional neural networks can't naturally handle this kind of irregular, non-Euclidean data. That's where GNNs come in, allowing us to model the true complexity of these relationships. Graphs are everywhere in our daily lives. Social networks map users and friendships, recommendation systems connect users to products, chemistry uses graphs for atoms and bonds, and transportation systems rely on locations and routes. Even knowledge graphs, which power search engines and AI assistants, are built on these principles. The key insight is that in graphs, a node's meaning comes from its connections and neighbors. This relational structure is what makes graphs so powerful and so challenging for traditional AI. GNNs are designed to unlock this potential. At the heart of GNNs is the concept of message passing. Imagine moving to a new neighborhood. You learn about the community by talking to your direct neighbors, hearing what their neighbors are saying, and gradually understanding the whole community's dynamics. In GNNs, each node prepares a message based on its current state, collects messages from its neighbors, combines them to update its own representation, and repeats this process multiple times. This allows information to propagate through the network, helping each node build a richer understanding of its context. Let's break down the message passing mechanism. First, each node creates a message based on its current features. Then, it aggregates messages from its neighbors. Think of this as collecting information from those around you. Next, the node updates its own state using this aggregated information. This process is repeated across multiple layers, allowing information to flow further through the network. Mathematically, this is often written as the new state of a node equals an update function applied to its current state and the aggregated messages from its neighbors. This is how GNNs capture the complex dependencies in graph data. Traditional neural networks, like CNNs, work well with grid-like data such as images. But graphs don't have a fixed structure. Each node can have a different number of neighbors, and the connections can be highly irregular. GNNs adapt their operations to each node's local connectivity, making them uniquely suited for graph-structured data. This flexibility is what sets GNNs apart and allows them to tackle problems that other neural networks simply can't handle. One of the most popular and foundational GNN architectures is the Graph Convolutional Network, or GCN. GCNs apply convolutional operations to graphs, similar to how CNNs work with images. They compute a weighted average of each node's neighbor's features, allowing the network to learn from local structure. GCNs are simple yet effective for many tasks, making them a great starting point for anyone new to GNNs. Graph Attention Networks, or GATs, take GNNs a step further by adding attention mechanisms. Instead of treating all neighbors equally, GATs learn which neighbors are most important for each node. This means different connections can have different weights, making the model more expressive and better at capturing complex relationships. GATs are especially useful when some connections are more informative than others. GraphSage is designed to handle large-scale graphs efficiently. Instead of aggregating information from all neighbors, GraphSage samples a subset of neighbors for each node. This makes it scalable and suitable for dynamic graphs, where the structure can change over time. GraphSage also supports inductive learning, meaning it can generalize to unseen graphs, a crucial feature for real-world applications. Message Passing Neural Networks, or MPNNs, provide a general framework that covers many types of GNNs. They explicitly define the message, aggregate, and update steps, making them flexible and customizable for different tasks. MPNNs are a powerful tool for researchers and practitioners who want to experiment with new ways of processing graph data. GNNs can be used for a variety of tasks at the node level. For example, node classification involves predicting the category of each node, such as identifying user types in a social network. Node regression might predict a continuous value, like a user's influence score. These tasks leverage the rich information available in each node's neighborhood, making predictions more accurate and context-aware. At the edge level, GNNs excel at tasks like link prediction and edge classification. Link prediction is used in friend recommendation systems, where the goal is to suggest new connections between users. Edge classification can identify the type of relationship between nodes, such as distinguishing between different kinds of interactions. These capabilities are essential for building smarter, more responsive networks. GNNs also tackle graph-level tasks, where the goal is to make predictions about entire graphs. For example, in chemistry, GNNs can predict whether a molecule has drug-like properties or estimate its toxicity. These tasks require the model to aggregate information from all nodes and edges, capturing the overall structure and properties of the graph. The depth of a GNN determines how far information can travel in the network. With one layer, a node understands its direct neighbors. 2 layers allow it to learn about neighbors of neighbors, and so on. This is called the K-hop neighborhood. However, using too many layers can lead to oversmoothing, where node representations become too similar. Finding the right balance is key to effective GNN design. One of the most impactful applications of GNNs is in social network analysis. GNNs power friend recommendation systems, help detect communities, maximize influence, and even spot fake accounts. By analyzing the structure and dynamics of social networks, GNNs can uncover patterns that are invisible to traditional methods, making online platforms safer and more engaging. GNNs are revolutionizing recommendation systems, like those used by Amazon and Netflix. By learning from user-item interaction graphs, GNNs can provide more accurate and personalized recommendations. They can also handle session-based recommendations, adapting to users' changing preferences in real time. This leads to better user experiences and increased engagement. In the fields of chemistry and biology, GNNs are used to predict molecular properties, discover new drugs, and analyze protein interfaces. They can even help in material science by modeling the structure and behavior of complex compounds. By representing molecules as graphs, GNNs unlock new possibilities for scientific discovery and innovation. Knowledge graphs are another area where GNNs shine. They power question-answering systems, enable semantic search, and help detect fraud in financial networks. By modeling entities and their relationships, GNNs can extract meaning from vast amounts of interconnected data, making information retrieval smarter and more efficient. GNNs are making waves in computer vision too. They're used for scene graph generation, point cloud processing, and even image classification via region graphs. By understanding the relationships between different parts of an image, GNNs can provide deeper insights and improve the accuracy of visual recognition systems. In transportation and urban planning, GNNs help predict traffic, optimize routes, and plan infrastructure. By modeling cities as graphs of locations and routes, GNNs can analyze complex systems and provide actionable insights for smarter, more efficient urban environments. Let's look at a concrete example: social network fraud detection. Imagine a network where each node is a user with features like age, join date, and activity, and edges represent friendships. The GNN starts by initializing each user with their raw features. In the first message, passing layer, users exchange information with their direct friends. In the second layer, information spreads to friends of friends. By the final step, each user's representation incorporates the broader network context, helping the GNN flag accounts that look normal individually, but suspicious in their connections. In fraud detection, the GNN learns that fraudsters often connect to other suspicious accounts, while legitimate users have diverse, well-established connections. It can also spot suspicious patterns in connection, timing, and density. By analyzing these relational patterns, the GNN can flag accounts that might otherwise go undetected by traditional methods. If you're ready to try GNNs yourself, there are several popular libraries to choose from. PyTorch Geometric is the most popular and is based on PyTorch. Deep Graph Library, or DGL, is framework agnostic and works with multiple backends. Spectral is a great choice if you prefer TensorFlow or Keras. These libraries make it easier to build, train, and experiment with GNNs on your own data. Working with GNNs comes with its own set of challenges. Graph data is irregular and can be memory-intensive, especially for large graphs. Efficient sampling strategies are needed to handle big data sets. It's important to start with simple GCN architectures, use appropriate normalization, monitor for oversmoothing, and choose aggregation functions carefully. These best practices will help you get the most out of your GNN models. The future of GNNs is bright, with ongoing research focused on scalability. Better sampling techniques, distributed training approaches, and efficient attention mechanisms are making it possible to train GNNs on ever larger graphs. These advances will enable GNNs to tackle even more complex and ambitious problems in the years ahead. Researchers are also working to increase the expressive power of GNNs. This includes developing models that can handle higher-order graph structures, better positional encodings, and subgraph-based approaches. These improvements will allow GNNs to capture even more nuanced patterns and relationships in complex data. GNNs are increasingly being integrated with other data modalities, such as text, images, and time series. For example, combining graph and text data powers knowledge graphs, while graph and image integration enables scene understanding. Dynamic graphs that evolve over time are also an exciting area of research, opening up new possibilities for AI applications. A deeper theoretical understanding of GNNs is emerging. Researchers are exploring the limitations of GNNs, their connections to graph theory, and the guarantees they offer for generalization. This foundational work is essential for building more robust and reliable GNN models that can be trusted in critical applications. GNNs are finding new applications in scientific discovery, financial risk modeling, supply chain optimization, and cybersecurity. As more real-world problems are recognized as inherently graph-structured, the importance and impact of GNNs will only continue to grow. These emerging fields highlight the versatility and transformative potential of graph-based AI. Graph neural networks represent a fundamental shift in how we approach machine learning. Instead of focusing on individual data points, GNNs help us understand systems of interconnected entities. The ability to learn from relational patterns makes GNNs uniquely powerful for understanding complex systems, where the whole is truly greater than the sum of its parts. As we continue to explore the interconnected world of graph AI, GNNs will play an increasingly vital role in solving real-world problems.